All right, so now we're going to take a look at another way by which we can calculate the the enthalpy change for a reaction, and this is by using something known as the bond enthalpy, which we describe as the enthalpy change that's associated when we break a bond in 1 mole of a molecule in the gas phase, right? So the energy or the enthalpy specifically needed to break those bonds. So for instance, we have here a molecule of H2 hydrogen gas, or hydrogen in the gas phase, turning into hydrogen atoms. Well, what has to happen in order for that process to occur? Well, if you remember, hydrogen Lewis structure looks like this. Okay, what we need to do is we need to break this bond here. And then when we break that bond, we end up with individual hydrogen atoms as a result, right? So the energy or the enthalpy needed for that process is what the bond enthalpy is. And again, here our little degree sign means these are standard conditions. Standard bond enthalpy, in this case for hydrogen, is 436.4 kilojoules per mole of the H2 in the gas phase. All right, so these values, the bond enthalpies, just like other enthalpies of formation, these are tabulated, and we can look them up in any appendix in any chemistry textbook, and they're in your textbook as well. So what this means is if we have a reaction, chemical reaction, we can actually look, and again, this applies specifically now to your covalent molecules, where we actually have covalent bonds involved, kind of like these. We can look at the total bond enthalpy for the reactant side and the product side of that equation, and we can apply that to a very simple equation. So the bond enthalpy then, or the enthalpy change, I'm sorry, for that reaction would be simply equal to the sum. So remember our little sigma sign there, that means the sum of the bond enthalpy. So BE is how we abbreviate that, bond enthalpy for the reactants. And then we're going to subtract the bond enthalpy, the sum of the bond enthalpy for the products. All right, so you'll notice here that the bond enthalpy, these are all positive values. Okay, so this amount of energy is needed to break that bond, which means when bonds form, that energy gets released. So, and that would then mean that the sign becomes negative. So the way that we address that in our equation is we write that equation this way. So the bond enthalpy for the reactants minus the bond enthalpy for the products, and we just simply add together this, all of the bond enthalpies for the reactants, that's a positive value. We add together the bond enthalpy for the products, that's a positive value, and we just subtract reactants minus products is going to give us the bond enthalpy for that reaction. So in other words, the way that we look at this is the total energy input to break the bonds in the reactants. Subtract from that, we're going to subtract total energy released. Energy gets released when bonds are formed in the product side of that reaction. So let's take a look at some examples of some other bond enthalpies, and you'll see this table in your text in chapter 10. I believe in your appendix, there are some other bond enthalpies as well. And these are the most common types of covalent bonds you'll see. So we just looked at the hydrogen-hydrogen bond in H2, and that has a bond enthalpy of 436.4. And these are always reported in kilojoules per mole of that original reactant, or that original bond that we're looking at. So the hydrogen-nitrogen covalent bond has a slightly lower bond enthalpy of 393. If you take a look at some of the other ones, you will see that some of them have significantly higher bond enthalpies, and they sort of correlate to some of the trends we saw back in the earlier section. So for instance, if we compare the bond enthalpies for nitrogen bonds, single bond versus double versus triple bonds, you will see that the bond enthalpy for the triple, right, is significantly more than the double, and that's significantly more than the single bond, right? And as we know, if we're comparing two atoms that are similar and they're connected by covalent bonds, multiple bonds are stronger than individual bonds. In other words, a triple bond is generally stronger than a double bond, which is generally stronger than a single bond. That's exactly what we see in these values here. The triple bond requires a lot more energy to break than a double, which requires more energy to break than a single bond. So when we calculate our bond enthalpies, or the enthalpy change for a reaction based on our bond enthalpies, we're going to come up with similar overall changes. So our delta H for the reaction could be negative, in which case it's an exothermic process, or the delta H for the reaction could be positive, in which case it could be an endothermic process. So let's take a look at an example. We're going to use some of those bond enthalpies to calculate the enthalpy for this reaction. All right, so we have here now this reaction between methane and oxygen to produce CO2 and H2O. So here we want to make sure, again, ensure that it's balanced. Whenever you use any chemical equation, you want to make sure that the equation is balanced, because we are going to now figure out what types of bonds need to be broken, what types of bonds need to be made in order to go from the reactant side to the product side. So if I take a look at my CH4, right, we know that CH4 at this point, we have our Lewis structure, carbon, and 4 H's around it. So I have CH bonds in this molecule. And how many do I have? I have 1, 2, 3, 4. So that means I would need to break those 4 CH bonds. In the case of O2, the oxygen molecule, so I have here my O2 Lewis structure, right? So it's a double bond between the oxygens. And I have 2 of these. So what I'm doing here is I'm breaking 2 times the oxygen double bond. Okay, and I can look these up immediately here so that we don't forget to do this down the road. So my carbon to hydrogen bond, that is over here, single bond. So that's 414 kilojoules per mole. So I can insert that right away. So 4 times 414. And then this is where the stoichiometry of the balance equation is going to be important. I'm breaking 2 of these oxygen double bonds. Okay, so that's this one here. So I have 2 times 498.7. 2. And then I end up making, so the products now in this reaction, on the right side, I have CO2. Okay, so carbon dioxide, Lewis structure looks like this. And it is important that you draw the correct Lewis structure so you know what types of bonds you're breaking. So here I have a CO double bond and I have another CO double bond. All right, so I'm making now 2 carbon oxygen bonds, double bonds, and I can look that up over here. Let's see. It's this one. That's 745. And then the other thing that I'm making are 2 H2Os. All right, so remember now your H2O. Hopefully at this point, the structure of water is emblazoned in your brain. So we get 2 H2Os. So in water, I have my oxygen between 2 hydrogens. And I have 2 of these. So I have an oxygen-hydrogen bond here. I have another oxygen-hydrogen bond. I have 2 OH bonds in 1 water molecule. So that means I would have a total of 4 of them in 2 water molecules. I have 4 OHs. Right, so let me reiterate that. In 1 H2O, we have an OH bond on one side and an OH bond on the other. So we have two OH covalent bonds in one water molecule, but I have two of them based on the stoichiometry in this equation. So 2 times 2 would be 4 OHs. So I look up the OH bond. Where is that one? The OH is over here at the top. So that's 460 kilojoules per mole. All right, all I'm doing is then adding these up on the reactant side and the product side. You'll need your calculator in order to do this. All right, so we substitute these values. We have 4 times 4, 14, plus 2 times 498. All right, so our delta H now for this reaction would be 4 times 4, 14 plus 2 times 498.7. So that's the bond enthalpy for the reactants minus the sum of the bond enthalpies for the products. Oh, there's a little asterisk here. I'm sorry, I didn't see this. So it says the bond enthalpy in CO2. Okay, so this is important because this actually affects our molecule. This is the asterisk that we see up here, this one. So in CO2, that carbon-oxygen double bond is actually not 745, it's actually 799 kilojoules per mole. Okay, and that's specific for CO2, so we need to change that. This should be 799. And then we're going to add that to the bond enthalpy. So they have 4. So 2 times 799 plus 4 times 60. Substitute all of those into our calculator, and we get the delta H for this reaction as negative 785 kilojoules per mole, right? Which tells us that this being a negative value now, right, this is an exothermic process. Okay, so in order to use the bond enthalpies to determine the delta H for the reaction, you need to know the types of bonds involved, which means you need to draw the Lewis structures for each of the reactants and products. Pay attention to the stoichiometry, right, of this equation, right? So we're keeping track of the fact that we have, in this case, we have two of the O2 molecules on the left side. And we also have 2 of the H2O molecules on the right. So we need to multiply whatever number of bonds that we have there by that stoichiometric coefficient to get the correct number of bonds that we need to either break or that we need to make. And then we substitute into our equation. So the bond enthalpy for the reactants minus the bond enthalpy for the products, which again seems simple enough, but again, you want to make sure that you keep track of the fact that you're subtracting. In this case, you're subtracting the reactants minus the products, and that'll give you the delta H for this particular reaction, or any reaction that involves using the bond enthalpies. And again, bond enthalpies, you do not need to memorize those. Okay, you can look them up in your tables, or if you need them on an exam or a quiz, or an exam especially, you'll be provided with those.